Have you ever wondered if the beam you're using is actually strong enough to handle the load? In this video, I'll break down the moment of resistance of an I-section beam step by step. Using a simple formula and real calculations, we will see if this beam is safe or if it is at risk of failure. Stick around to master this essential engineering concept. By the way, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London, and in here we talk about structural engineering. This example is about moment of resistance of I section, and I section is an unsymmetrical section. We have to determine if this beam, which is shown over here, is adequate to support applied loading, which is 60 kilonewton. And here allowable fiber stress is 15 Newton per millimeter square. And I've taken this example from this book. The section size is given over here. Have a look that this section size is not symmetrical. That will mean that the top portion will have more moment of resistance as compared to the bottom one. Let us see how we can solve this problem. For solving this problem, I will be using famous flexural formula, which I remember it by saying stress is equal to mi over I, where m can be either applied moment or it can be moment of resistance. Here, allowable stress is given to us, which is 50 Newton per millimeter square, and the section is given to us, which means that we can find out the second moment of area, and we can find out this y as well. I call it as y bar, which means that it is a centroid of the section. So the formula for centroid of this section is y bar is equal to summation of ay divided by summation of a. This will mean that I will divide this portion into number of areas, and then I will find out y bar. Ixx is second moment of area of the compound section. This will be equal to summation of Ixx of individual components plus summation of a y bar minus y whole square. This is what we call as parallel axis theorem. So we will use these formula to work out moment of resistance, where from this formula I can say that if I want to find out moment of resistance, then moment will be equal to sigma into I over y or y bar. So here stress is given to us, and all I need is second moment of area, which in this case will be Ixx compound section, and y bar, which means that it is the centroid. So let us see how we can find out these values. But for this, I have to divide this section into number of different areas. So let us see how I can divide this section. So here I can say that this is the first one, and this is the second section, and this is third section. In this way, I'm able to divide it into three parts. So first part is 200 by 60, second part is this 300 by 50, and third part is 200 by 60. So let us put these values in a table, and from there we can work out y bar, which is the centroid, and from there we can work out the second moment of area of compound section as well. So let us go and set up a table. First I will say part number, and here I will draw a line, and secondly I will say area. Area is in millimeter square, and then distance y, and then I have a times y, and the unit will be millimeter cube, and Ixx, the unit will be millimeter power 4, and I will have y bar minus y, and unit will be millimeters, and finally I will have y bar minus y square, and unit will be millimeter power 4. In this way I have set up this table, and now I will write the first part number, and I will draw a line as well over here. So first part is 200 by 60, This is part number 1. Part number 1 is over here. It is this part, the top one. Part number 1 is 200 by 60 and part number 2 is 300 by 50. Let me write that down. 300 by 50, and then I will draw a line over here again. Third part is the bottom one, and bottom one is this one. It is 60 by 100, and then I will draw another line over here. And finally, here at bottom, I will have summation of areas. So here I will have summation of area. And here at this place, I will have summation of AY. And in here, I will have summation of IXX. And at the end, I will have something as well. So the first area will be the 60 times 200. So 200 multiplied by 60. This is equal to 12,000. And then I will have 50 times 300, which is area of this part. This will be equal to 15,000. Then I will have 100 into 60. This will give me 6,000, and in total I will get 33,000 as summation of area. Now we have to find out y. Y is distance from center of a particular area to bottom datum line. When we are trying to find out centroid, then we have datum line. So let's see how we can do that. If I come over here, y1 will be equal to distance from center of this area all the way to bottom. So I need this distance, and to find this distance I need half of this distance, which is half of 60 is 30. So total distance from top to bottom is equal to 420, which means 300 plus 60 plus 60, when total is 420. If you take away 30 from 420, the remaining one will be 390. So I can say that y1 is equal to 390. And how about y2? Y2 is distance from center of second area all the way to bottom. Distance from second area to this point is half of 300, which is 150. So 150 plus this distance is 60. So 150 plus 60 will give me 210. So I can say y2 is equal to 210. This is millimeters and this is millimeters as well. Now y3 is pretty obvious, which is half of this bottom area. So this distance is 60. So half of 60 is 30. So I can say that y3 is equal to 30 millimeter. So now I have y2, I have y1, and I have y3. Let us see how we can put these values over here. So remember these three values: y1 390, y2 210, and y3 30. So let's put these values back in here. So y1 was 390, and this was 210, and this was 30. Once we have got these two values, then we can multiply a area with y. So when you multiply these two values, this and this, you will get 4.68 into 10 raised 6. 4.68 times 10 raised 6. When you multiply 15,000 with 210, you will get 3.15 into 10 raised 6. When you multiply 6,000 with 30, you will get 0.18 into 10 raised 6. And you have to add them together. So 4.68 plus 3.15 plus 0.18. I'm getting 8.01. So this is 8.01 into 10 raised 6. Once I've got these values, then I will get IXX. And as you remember previously, that if you have a rectangular section, for rectangular section, if you recall, for rectangular sections, if this is B and if this is D, I is equal to BD cube over 12. There's a cube in D. For the first one, B is equal to 200 times D is equal to 60 cube divided by 12. Whatever value I get, I will put over here. And in the same way, I will find out values for the second part and third part as well. So for first part, it comes out to be 3.6 into 10 raised 6. And I'm using the same logic. And here B is 50 and D is 300. So BD cube over 12. It means that 50 times 300 cube over 12. And the value which I'm getting is 112.5 into 10 raised 6. And finally, for third one, it's very simple. 100 into 60 cube divided by 12. And I'm getting here 1.8 into 10 raised 6. And now I have to sum up these values. 3.6 plus 112.5 plus 1.8. I'm getting 117.9 into 10 raised 6. Once I've got these values, then I have to find out, first of all, y bar. Here, I need y bar over here, but I don't have y bar. Y bar is distance from centroid of the entire shape. If I go back here, this is distance from center of this entire shape to bottom. So for this, I will use this formula. Y bar is equal to AY over A. So let us use this formula and find out Y bar. So Y bar is equal to summation of AY divided by summation of A. Summation of AY is this value, 8.01 into 10 raised 6 divided by 33,000. Let us see what value do we get. I'm getting 242.73. So 242.73 millimeter. Now I will use this value to find out y bar minus y. 242.7 minus 390. So I'm getting here minus 147.3. Using the same logic, 242.73, take away 210, I'm getting 32.73. And here 242.73 minus 30, this one is simple, 212.73. Now all I have to do here is I have to multiply this area, which is 12,000 minus 147.3 square. I will get some value over here, and here it will be 15,000 times 32.73 square. I will get some value here, and here it will be 6,000 times 212.7. I'm getting 260.37 to 10 raised 6. And for second one, I'm getting 16.069. And finally, I'm getting 271.48. And when you sum this up, this is a y bar minus y square, 547.92 into 10 raised 6. Once you have got these values, then you will use this formula. Ixx of compound section is equal to summation of Ixx plus summation of a y bar minus y square. And Ixx compound, I simply call it Ixx. Summation of Ixx is 117.9 into 10 raised 6 plus summation of ay is 547 0.92 into 10 raised 6, 665.8 into 10 raised 6. Now I have distance from centroid, and now I have Ixx or I. From here, I can work out the moment of resistance top and moment of resistance bottom. Before I do that, this Y bar is distance from bottom. How about distance from top fiber? So we need stresses in top fiber and stresses in bottom fiber. Now you can see here that we have Y bar, which is distance from bottom fiber to centroid. It is this distance, which is Y bar from the bottom, 242.73. If I wanted a distance from the top, then it will be this entire distance, which is 420. From top fiber, it would be 420 take away 242.73. So that's what I'm going to use over here. If I say moment of resistance top, and I'm using the same formula as I mentioned earlier, which is this one, stress is equal to my over I, and from here we can find out moment of resistance is equal to stress times I over Y. So I can say moment of resistance top, I can say this is MR top is equal to sigma into I over Y. Sigma is equal to 50. I we just found out 665.8 into 10 raised 6. Y for top is this value 420 minus 242.73, and I want to convert this entire bit into kilonewton into meters, so that's why I will multiply with 10 raised 6. This will give me MR top. Let's see what value do we get. I'm getting 187.8 kilonewton meter. This is MR top. And similarly, moment of resistance bottom, MR bot, is equal to sigma into I over Y. Sigma is 50. I is 665.8 into 10 raised 6 divided by, from bottom, the value is this one, 242.73. And the entire bit, I want to convert it into kilonewton into meter. This will give me 137.1. As expected, because there is more material on the top side, so it will have more moment of resistance. Now, when we are designing something, we always compare moment of resistance or capacity of the section with the applied moments. How do we find out applied moment over here? The loading applied here is 60, so reaction here will be 30 kilonewton, half of that, because loading is applied at the center, and applied moment M is equal to force times distance, and maximum moment will be at the center, so force times perpendicular distance. Force reaction here is 30 and distance is 3. So in this way I get 90 kilonewton meter. Or if you wanted to use a direct formula when there is a central point load, is this one. If you have P over here, and if this is L over 2, this is L over 2, this is P over 2, this is P over 2, moment is PL over 4. So P here is 60, L is 6 divided by 4. In this way, we get 90 kilonewton meter as well. So it's one and the same thing. Either you use the formula directly or use common sense that if the load is applied at the center, it will be equally divided between supports, and from support to point of application of load, it will generate a moment. So reaction times the distance, it will give you moment. Now look at this one. The moment of resistance at bottom is 137. At top, we have this value 187. M, which is equal to 90 kilonewton meter, is less than MR top, which is equal to 187.8 kilonewton meter, and it is also less than MR bottom, which is 137.1 kilonewton meter. In this situation, I can say that this beam is safe. This beam is okay. So whenever the applied forces are less than the capacity or resistance, in that case, we say that it is a safe beam. In design at a very basic level, at least we do this thing that we compare applied versus the resistance. So here in this case, applied versus resistance is less, which means that the beam is safe. In this way, we were able to find out moment of resistance with the help of one basic formula that you need to remember, and that basic formula is this one: stress is equal to my over I. The way I remember it, that my means me and I means me as well. So whenever some bending is happening, then you use this formula. If there is axial compression or tension, then you use stress is equal to P over A, or force over area. This is for axial forces. So these two formula, they are the backbone of all engineering design. Thanks for watching this tutorial today. I will see you in my next lecture. Thank you.